All right, here we are, Thursday morning. Finally, we're getting to the important parts of the climate system. The ocean, that's where all the action is. Now, since the Industrial Revolution, we've started putting greenhouse gases into the atmosphere. The climate system has gained heat. Who can tell me what percentage of that heat has gone into the ocean? Most? That's the best answer we've got so far. The answer is it must be over 90%. The best estimate from a few years ago was 93% of that heat's gone into the ocean. And it's gone into the ocean because the heat capacity of water is much larger than the atmosphere, and the density of that water is much larger than the atmosphere. So it takes a lot more heat to get the water in the ocean to be increasing by 1 degree centigrade than the atmosphere. So over 90% of that heat's gone into the ocean. Now, what about CO2 itself? What percentage of CO2 that's been put out since the Industrial Revolution has gone into the ocean? How many? No, that's a little high. In round numbers, about 25% goes into the ocean. That's what makes the ocean more acidic. 25% has got taken up by the land, so he's important occasionally. And about half has been left in the atmosphere. So only about half of the CO2 that's got put out has remained in the atmosphere. So here we are. The ocean takes up over 90% of the heat, 25% of the CO2. Every morning when you get up, you should say a little prayer of thanks to the ocean. I say a little prayer of thanks to the ocean because I spent my whole career at NCAR studying it in a building that's at 6,100 feet. That's pretty good. And I've enjoyed it. So we're going to talk about parameterized physics. If I can get it to advance. Here we go. So there's quite a lot of parameterizations in the ocean model, but in the time I've got, I'm only going to talk about two. One is vertical mixing, and the other is lateral mixing. The ocean is driven from above. It's driven by wind stress from above. So it's unlike the atmosphere, which mostly gets driven from below, heating at the surface from below. So the winds drive the ocean, and they drive a whole bunch of turbulence in the upper ocean. That turbulence produces what's called the mix layer, a uniform region of uniform temperature at the top of the ocean by mixing downwards. And then below the thermocline, which is the region where the density and the temperature salinity of the ocean changes dramatically as you go down, then you get to the ocean interior, where there's a very small amount of mixing. So the vertical mixing scheme in the ocean model is called KPP, K-profile parameterization. And it's been in there since the start of this project. It was first published in 1994 by people from NCAR. And it says that the unresolved turbulent vertical mixing due to small scale overturning is parameterized as vertical diffusion. It is guided by studies in the atmosphere so that the time rate of change of a component is minus the vertical gradient of the eddy fluxes in the vertical, and those eddy fluxes are parameterized as a coefficient times the vertical derivative of the quantity itself. You put those two together and you get time rate of change of a quantity is vertical diffusion. And the Kx represents an eddy diffusivity or eddy viscosity. But the innovative thing about KPP is that it wasn't just a vertical diffusion scheme, because the scalars, the temperature and salinities in the ocean, have these lone local or counter gradient terms. This was new in the formulation of KPP and is important in what it produces. So there's three high-level steps for KPP: determining the boundary layer depth, D, calculation of the interior diffusivities, which are below the boundary layer and small, and then you evaluate the diffusivities in the upper boundary layer where they're larger. That diffusivity throughout the boundary layer depends on several things, but in particular on the surface forcing. So the stronger the wind driving, the stronger the winds, the stronger the turbulence that's going on in the upper ocean. And also a new thing about KPP was it produced quite large diffusivities below the boundary layer, which mixes temperature and salinity quite deep in times of very strong surface wind stress, such as atmospheric storms. The previous things to KPP had only really had the strong mixing in the boundary layer itself. KPP had quite strong mixing below the boundary layer, which then got the heat that's been produced and coming into the ocean, deeper into the ocean. So this ocean model could take up more heat, just as I said it should, than previous implementations of a vertical mixing scheme. So how do you calculate the boundary layer depth? The boundary layer depth D is the minimum depth in the ocean where the bulk Richardson number, reference to the surface, is a critical value of 0.3. So the bulk Richardson number is defined as the difference between the surface buoyancy and the buoyancy at depth D times the depth itself, divided by the square of the difference in the velocities plus an unresolved shear. So you calculate in the ocean model, you go down layer by layer until the Richardson number, bulk Richardson number, hits this value 0.3, and then that determines the boundary layer depth D. So this Richardson number measures the stability of stratified shear flow. So the idea is that boundary layer eddies with a mean velocity at the surface VR and buoyancy at the surface VR should be able to penetrate to the boundary layer depth D, where they first become stable relative to the local buoyancy and velocity. So that says you're given a buoyancy and a velocity at the surface that can mix stuff down to a depth D, where they could become stable compared to the buoyancy and the velocity at that depth. So once you're below the boundary layer, the interior diffusivities are all small until you get to convection. Convection means that when the density could perhaps be greater above a place where it's less, then vertical mixing occurs by convection, because you need the density to always be getting lighter as you go up for stability. Other than that, these other values, internal wave breaking, double diffusion, are all relatively small. So how does this work in practice? This is a plot from the KPP paper, 1994, and it's a verification at Ocean Station Papa, which is in the North Pacific. Largest was from Canada, so this was the Canadian ship that's off in the North Pacific. And over a year, it had observations of temperature down to a depth of 150 meters. And what happens is that as the spring and summer come on, you get more and more heat coming into the ocean. So the SST, the sea surface temperature, increases and keeps on increasing. And in the end, it gets mixed down more and more, especially in the fall, where you have strong winds and storms. So the mixed layer depth decreases, gets larger and larger, goes deeper all the way through November. Then the heating is gone, so the ocean's losing heat, go back, and in the end, the mixed layer depth shallows again to here. And this is what the KPP model produced in that simulation. And you can see it's reasonable without being perfect, which is just what the ocean model and the climate model is all about. Now, I want to spend the rest of the time talking about my favorite parameterization in the ocean model, which is the mesoscale mixing of traces, ocean temperature and salinity. And this was something that I first proposed with my colleague Gent-McWilliams in 1990. But if you want to read about it and understand it, make any sense of it, this is the one you should read. In 2010, I was asked to write a review of GM parameterization, which I call is 20 years after it had been proposed. It's called 2020 hindsight. And if you want to understand it and have some interest in what it did to the CSM model, this is the paper to read. So, in the ocean, the mesoscale eddies and the biggest amount of energy goes into the mesoscale eddies, which have scales of at most 100, 200 kilometers, but most places they have scales which are much smaller. So if you run an ocean model and you want to call it such that it resolves the eddies, you have to have a horizontal resolution of 1/10 of a degree. The simulation from a GFDL climate model with a resolution of 1/10 of a degree. And you can see there's all sorts of variability. This is the tropical Pacific, these are tropical instability waves, but there's variability on small scales all over the world's ocean. Unfortunately, in a climate model, you cannot afford 1/10 of a degree resolution in the ocean component. Though most climate models still of the day, in fact, use a 1 degree or about 1 degree. Some have gone down more now as computers have improved to 1/2 degree, occasionally 1/4 degree, but still a lot of them use a resolution of about 1 degree. And here's a simulation using a 1/10 of a degree. And as you can see, this is South Africa. This is the Agulhas current coming and retroflecting around here. There's a lot more variability in this one than that one. So a 1 degree model does not resolve the first baroclinic deformation radius except right at the equator. And hence it misses, there's a lack of the mesoscale turbulence, which mixes temperature, salinity, and passive traces. And what's the reason that the Rossby radius of deformation is so much smaller in the ocean than in the atmosphere? And the answer is, it's because of the vertical density gradient. In the atmosphere, you start with the surface density, and as you go up, by the time you get to the tropopause, the density is about 1/10 of what it is at the surface. So you have quite a large vertical temperature gradient. And that means the Rossby radius of deformation, which is where things get excited and all the energy is on the scale of a few thousand kilometers. That's the scale where the lows and highs of the atmosphere are produced. In the ocean, at the equator, where the surface water is the warmest, the difference between the density at the surface and the density at the bottom of the ocean is 1 or 2%. And then when you go further north and south towards the poles, where the surface water is colder, the difference of the density from top to bottom is even smaller than that. That very small vertical temperature gradient means the Rossby radius of deformation is like 200 kilometers at the equator. But as you go towards the poles, it goes down to something like 10 or 20 kilometers. That's why you need a resolution of 1/10 of a degree in the ocean to produce all the mesoscale eddies and all the energy. So in an ocean climate model, the effect of those mesoscale eddies has to be parameterized. So why is GM needed? So ocean observations suggest that mixing along isopycnals are what we call the surfaces of constant density, isopycnals in the ocean, that the mixing along it is order 10 to the 7th times as large as the mixing across the isopycnals. In the ocean, there's very, very small mixing across the isopycnals. So the water masses retain their identity once they're formed over months, years, tens of years even. So there's very little mixing across the isopycnals. And in the early ocean models, the effects of the eddies were parameterized as horizontal diffusion along at constant depth. And that's because they were depth, the vertical coordinate was depth. So the isopycnal slopes in the ocean are at most something like 10 to the -3, 10 to the -4. But that's smaller than the difference 10 to the 7. So if you have diffusion along here, it produces cross-isopycnal diffusion larger than we want in ocean models. So this horizontal mixing results in excessive diapycnal, which is cross-isopycnal mixing, which degrades the ocean solution. So it was recognized in the 80s that you needed to orientate this diffusion of temperature and salinity instead of along a depth, constant depth, along constant isopycnals to be consistent. So that was implemented. But in 1990, McWilliams and I proposed that as well as this diffusion along isopycnals for temperature, that the effective eddies had an advective component as well as a diffusive component. So we proposed that temperature and salinity should be advected by the mean flow and by this eddy-induced velocity. That's what we called it. And this velocity was dependent on the ratios of the horizontal density to the vertical density gradients. So, need some water. Everybody needs. So, this is what we proposed. And how am I doing on time? So, this was a test case that we did where we had light water over dense water. And so these are lines of constant density. This is the stream function from that eddy-induced velocity, which will produce motions in an anti-clockwise direction when the density gradient is like this. So as you let it go, it produces motions like this. It flattens out the density gradient. And in the end, it produces this as an equilibrium solution where the density gradients are flat. And what it's done is it's reduced the potential energy of this system to a minimum value. So it's acting just like baroclinic instability does. It takes potential energy out of the system. And that's what mesoscale eddies are doing. They're formed by baroclinic instability. They take potential energy out of the system. And this is what's done by this eddy-induced velocity by producing these extra advections. So this effect is most important in the southern hemisphere. In the southern hemisphere, there's a current called the Antarctic circumpolar current, strongest current in the world's oceans, which goes all the way around the globe. It's the only current which does that. All the others are in closed basins. And so the dynamics of the Antarctic circumpolar current are different than all the mid-latitude oceans. And they're actually more like atmospheric dynamics, because you can go all the way around and it keeps going. So this Antarctic circumpolar current, here we got 80 south, 30 south, so Antarctica over here. And this is a schematic of the ocean in this region. All these things are called Antarctic bottom water. All these waters get labeled: Antarctic intermediate water, North Atlantic deep water. It's coming from the North Atlantic, rises up here. But this Antarctic circumpolar current is driven by a wind jet in the Southern Hemisphere. The Southern Hemisphere wind jet is located around here, and it's coming out of the board. It's going from west, it's called a westerly wind, so it's coming out from the west to the east. And the Antarctic circumpolar current is following it and also coming out of the board here. So what's happening? The wind drives the ocean coming out of the board here, and Coriolis is turning it, Southern Hemisphere, Coriolis is turning it to the left. So you've got drift at the surface, which is going from the south to the north. Now, that drift is strongest where the wind is the strongest and the current is the strongest. And it gets weaker as you get either side of the wind jet. So here you've got a stronger surface current here than here. So you have convergence of water here. So that water has to go down. It's opposite on this side of the jet, that the surface drift is weaker here than it is here. So you've got divergence here, so that means water has to come up. So the mean flow is producing an overturning circulation, which is clockwise, like this. That clockwise circulation is then producing the slopes in the isopycnals like this. Just from that previous slide, what we know is that the eddies should produce a circulation to counter that of the mean flow in an anti-clockwise direction like this. So what we want is a mean meridian overturning circulation, this direction, balanced by an eddy overturning circulation in this direction. So, in the first time that this parameterization was implemented in an ocean model was in like 1993. And you've probably heard of this name before. He should have been here on Monday. This is the first thing that Gökhan did when he came to NCAR. And as you can see, it's a very coarse resolution model, 4 degrees by 3 degrees, 20 layers. And we produced two solutions. One where we just had the old form of horizontal diffusion, and one where we implemented GM. So these are plots of the stream function of the meridional overturning circulation. So meridional overturning circulation you calculate by integrating zonally. So that takes out the U component of the velocity. And then you form a stream function from the northward velocities and the up and down velocities, V and W. So in this plot here, which is the overturning stream function, circulation is clockwise around the positive values, anti-clockwise around the dotted values. So this in the northern hemisphere, remember it's integrated, is what's called the overturning circulation, and it's almost all in the Atlantic. Everybody should have heard of the Atlantic meridional overturning circulation, which is what people think might decrease as climate gets warmer. So that's occurring mostly in the Atlantic. In the tropics, there are counterclockwise circulations here. But here is this circulation that I just talked about that's under the zonal, the wind jet, and it's going in this direction. Okay. And then when we put in the GM parameterization, we calculate the MOC just due to the mean flow. That's what we get here. There's not much change over a lot of the ocean. And here is still this overturning circulation due to the mean flow. But then when we calculate the overturning circulation due to the sum of the mean plus the eddies, we get this. Again, there's not much change over the most of the ocean, except right here, where the overturning stream function has been reduced enormously. So that what's happening here is the overturning circulation due to the eddies is almost exactly counteracting that overturning circulation due to the mean flow. And this only happens in the ACC. Elsewhere, the eddy-induced meridional overturning is really small. So this parameterization really improves and comes to the fore in the Southern Ocean. This is where it's the strongest. And what does it do? You can see here, this is a circulation in a clockwise direction. So at the surface, it's bringing surface cold water because it's farther north, south towards the Antarctic, north here. So you're getting cold water overlying warm water. So you're getting denser water overlying less dense water, and that produces convection because that's an unstable situation when the density gradient isn't reducing as you go up. So in this simulation, we get quite a lot of convection in this region because of this transport of cold surface water farther north. In this simulation, that's gone away. So when we produce, where does overturning circulation and deep water formation occur? In the horizontal diffusion case, it occurs in quite a few places, and in particular, it occurs in many places just where I've said it would because of this advection of cold surface water farther north. The GM, this has gone away. This was probably my favorite plot of my career because we never really expected this to work so well. Here, the deep water formation, where water from the surface is taken down below, occurs in just a few places. And if you asked an observing oceanographer, they would say they're actually pretty much in the right place. They're in the Weddell Sea, the Ross Sea, the North Atlantic, and the Labrador Sea. And that's where it's been observed to occur. And it was this plot that really persuaded us that this parameterization might have a real effect and improvement on climate models. So, in summary, Gent-McWilliams parameterization mimics the effect of unresolved mesoscale eddies as the sum of diffusive mixing of traces along isopycnals, which was first implemented in a model at GFDL, but also this additional advection of traces by the eddy-induced velocity. Scheme is adiabatic, and therefore it's valid in the ocean interior, where the vertical mixing is small, so this is really important. It's much less important in the surface ocean, where the vertical mixing scheme is much stronger. I said it acts to flatten isopycnals, thereby reducing potential energy, which is what baroclinic does. Instability does, takes energy out of the mean flow. And it eliminated any need for any horizontal diffusion in Z-coordinate ocean general circulation models. And the implementation of GM in an ocean component was a major factor enabling stable coupled climate model simulations to run without flux adjustments. So, a bit of history. The first version of the CSM was the first climate model to produce a non-drifting control run without flux adjustments. This is the plot from that paper that described this. The run was 300 years long. Once it adjusted over the first 10 years, the temperature at the surface hardly drifted at all over those 300 years. So what was done in early climate models was that you would set up the atmosphere and ocean components. You would let them interact by exchanging heat and fresh water across the surface. And if you started from a realistic simulation, very quickly, that simulation would drift and not maintain its validity. It would go off to some other climate state. And the reason was that the heat and water fluxes that the atmospheric component wanted were not the same as the heat and water fluxes that the ocean component wanted. So what was done is that those two things, and what the atmosphere and what the ocean wanted, were differenced. That was called a flux adjustment. And that flux adjustment was applied at every time step in a model. And it was only when you applied that flux adjustment that if you started off with a realistic climate, that you would maintain a realistic climate as the integration went forward. But this was basically a cheat because, as I said before, the fluxes that the atmospheric component wanted were inconsistent with the fluxes that the ocean component wanted, which meant that there was something wrong with either or both, mostly the atmosphere, of course, one or both. And it was actually, in those early days, it was the ocean that was off because this GM fixed it quite a lot. Those flux adjustments had their largest values right in that Southern Ocean where this made the biggest difference. And some of those flux adjustments were on the order of 250 watts per square meter at that Southern Ocean. They were huge. CESM1 produced a non-drifting simulation without the use of flux adjustments. It was in the late 90s. This was huge news in the climate modeling system. And we were accused of cheating because everybody else didn't think this could be done. In fact, we submitted a paper to Science documenting this, and it was rejected because one of the reviewers said, basically, it couldn't be done, and we had cheated, which we hadn't. Now, one of the reasons that we know that GM was really important in this is that very quickly, other centers started implementing it in its ocean component. And within a few years, other centers had also started to produce simulations that maintained the present day climate without flux adjustments. So as a history, this model and its first implementations in the late 90s was the first one ever to produce a simulation where you didn't need these flux adjustments. Now, in 2004, I was asked to give a talk about GM at a city in Ireland called Limerick. Now, we all know what a limerick is, as well as a city in Ireland. So I couldn't resist producing a limerick about GM. So here we go. There once was an ocean model called POP, which occasionally used to flop. But eddy advection and much less convection turned it into the cream of the crop. Thank you.
Insight into like the history of the model and how these things that seem almost impossible to overcome through like endurance and science.
So one of the most, probably the most famous climate modeler in the US, Suki Manabe, who just won a share of the Nobel Prize for physics, still going strong in his 90s. 2 years before we got this result, I was at a meeting and I asked him about flux adjustments. He said, climate models will never run without flux adjustments. So nobody believed at that point, even the best climate modeler, that it could be done. So we did it.
As you take your research forward, you hit challenges and you find
that will seem impossible to overcome, to realize that like together collectively and through perseverance, you can find things about the world that we didn't previously know and be able to help the community out. So Peter, we do have some time for questions. So I'm going to say people come to the mics when you've got a question for Peter. And yeah, please.
Okay. I guess my question is, and this might be like an uninformed question, but if we know that flux adjustments like weren't conserving like momentum and energy, then why was that accepted as okay for so long?
Because if you didn't use those flux adjustments, the, the simulation of climate that you got drifted really quite strongly away from the present day. So if you then changed it and say increased double CO2, what you would get is a slight difference. The differences you'll get by doubling CO2 produced a drift in the climate that was much smaller than the drift in the control run because you weren't using flux adjustments. So, and that was because those flux adjustments were, as I said, in places on the order of 100 or more watts per square meter, which is much, much larger than the difference in the heat input due to doubling CO2. So what people used to do is they would run, if they didn't use, there was a group here that at NCAR that didn't use flux adjustments, so that, for instance, then the surface temperatures of the ocean, the atmosphere, would be going down. Then they'd double CO2, and the temperatures wouldn't go down quite as quickly. And so the result of doubling CO2 they would get by difference in those two runs. GFDL and most other climate models shows the opposite thing, which is they use these flux adjustments so that their base model runs would maintain a constant or close to constant temperature. Then when they double CO2, it would go up. So that was a choice that people made, but most people chose to use these flux adjustments because then it looked better when their base case, the temperatures were horizontal on a plot, not going down. Whereas in the group here, when they double CO2, the temperatures were actually going down, even though they interpreted that as a warming. Those people like GFDL, the Germans were also keen on these flux adjustments. They'd worked enormously hard to get the components they had. And we all stand on the shoulders of giants. So people at GFDL produced those first ocean and atmosphere components. So they worked really hard. They wanted to use them. They wanted to see what doubling CO2 would do. So they chose to use these adjustments to produce these non-drifting stable solutions. That was their choice.
And you brought up a really good point, which is like the numerical representations we have in our models aren't necessarily like completely reflective of what we observe and our theoretical understanding of the world. They're the best we can do. So what we do is we build these tools to reflect and to be able to look into processes, but sometimes those numerical methods don't resolve it out the way we'd like them to. So we do things such as flux adjustment this is back in the 1990s, so that we can make it a useful model. Right, so we can still contain, and the same way we have different configurations of the model. Sometimes we just turn off the ocean, right? So we prescribe the SSTs. That's not the real world, but it allows us to be able to explore different processes. So the models, just because they have things that they get wrong, doesn't mean they're not useful. Yeah. So that was kind of the situation we're in.
There's a quote from somebody named Fox about it. economic models, which is all models are wrong, but some are useful. A good quote. Yes.
Well, you mentioned the necessity to use these mesoscale parameterizations, especially in the high latitudes, because the Rossby deformation radius gets so small. Have people tried to get around this by having like a variable resolution sort of ocean model that at the equator is more certain? At the equator, you can resolve it.
Yes, the answer is yes, but still, as you get that, the number of grid points that you use, even to produce a tenth of a degree near the high latitudes, is still sort of unacceptable in terms of how much computer time the ocean would take in the climate system. Now, as the computer time has increased, people have started doing a few of these climate simulations with a tenth of a degree ocean model. And CSM, in fact, has some that were produced in China. And so there are a few integrations where we go forward in time doing the same sorts of things, but with an eddy resolving ocean component. There's a lot of more variability in the ocean component. In general, it produces a few surprises, but it doesn't alter terribly the future evolution of the climate as we see it. So in the future, there'll be more and more of these eddy resolving, because eddy resolving certainly produces much more interesting and exciting ocean solutions than our tenth. Given the fact that something like a lot of other people want ensembles of solutions, we've got a large ensemble here now of 100 cases. So there's always a dichotomy between how much computer time you put into the resolution to get it more accurate and realistic, how much time goes into producing all the cases with 100 ensemble members.
I guess for like the long future projections and the paleoclimate runs, there's probably no chance of doing the eddy resolving sort of in
Not at this
the
point.
current state of things, right? Yeah.
Those eddy resolving solutions go out. I think there's one or two that go to 21 or 100. But to do something in paleo, you're SOL, I think, a bit at the moment.
Thank you.